We will start today's lecture from the point we left yesterday. So if you recall, we were talking about the universal approximation theorem, and we all agreed that in order to generalize any sort of functions, what we need to have is only the tower function, right? So with tower function, I mean this function, okay? This is also called as impulse function. So if you read in a text book, if you find that impulse function, please don't get confused. This is one and the same thing. We also agreed that this tower functions can be built using connections of neuron, okay? And the conclusion till now is, although a sigmoid neuron may not be able to generalize a complex function, a complex nonlinear functions, but the interconnections of sigmoid neuron can generalize any sort of function, okay? So we'll start with the agenda we have for feed-forward network. So here, in case of feed-forward network, the input will be a real input, right? So the input features, it can have any real number. This feed-forward network that we're gonna see, it is capable of doing classification as well as regression. So here also, it is somewhat similar to sigmoid neuron, right? But the new thing that we'll learn here is, with this feed-forward network, there comes a representation power of neural network. What do I mean by representation power? It simply means that with the help of this feed-forward network, we can generalize any sort of functions, any complex functions. Okay.
Ashutosh, one question. So in this task thing, right, where you said the output can be binary classification and multi-classification and regression. So in so far, whatever examples we have seen, you have always shown the examples of binary classification only, right?
Yes.
We have not seen any regression example.
Yes, we haven't.
Yeah, okay.
Yeah. But if you'll think, in a way, we have also taken an example of regression. If you'll recall, in the previous class itself, we were, in case of even cancer predictions, what we were saying, that what is the probability that this person is going to have malignant cancer or benign cancer. So there we were coming up with some real number. After getting the real number, we applied some threshold and we converted it as a classification problem.
Okay. Okay.
Right?
Yeah.
But yeah, we haven't seen any dedicated regression problem.
Okay. Right? Okay. That's fine.
Now, in case of feed-forward network, again, the learning algorithm will be gradient descent that we have already seen in case of sigmoid neuron. Here we'll add one flavor on top of it, and that is something called back propagation, right? And accuracy metric will still remain same. For classification, we will be relying on accuracy. For if it is a problem of regression, we will be relying on RMSE. Okay? So this is a brief outline that we will be seeing with respect to feed-forward network.
What does task-specific loss function means?
This one?
Yeah.
Loss function. So if you recall, when we were discussing about perceptron, our loss function was what? Square error loss.
Yeah.
Right. Then we graduated to perceptron. After perceptron, we've seen sigmoid neuron. So in case of sigmoid neuron, still we were using square error functions, but we also learned another kind of loss function, and we named it cross entropy function.
Yes.
Right. So this is loss function. Now, what I mean by task specific loss function is, if I am solving a problem of regression, then I will have one kind of loss function. If I'm solving classification, then I'll have another kind of loss function.
Okay. Okay. And will these loss function apply to every neuron in that network?
Actually, to be honest, this loss function is the objective function. the whole neuron. So just think that all the neurons in a neural network, they work as a unit. They all have one common agenda, that is to minimize the loss.
Okay.
Right. So this loss is not a property of a neuron, rather it's a property of network now.
Okay.
Earlier we were having only one neuron, right? So there was no point of saying network. It was just one neuron. But now we will be having multiple neurons. So just think that this loss function is a property of network of neuron, not just a property of single neuron.
Okay.
Now, if you recall in the yesterday's class, we saw this figure, right? The screen size and cost part. And we agreed that with the help of sigmoid neuron, we can't generalize this function. This is a highly nonlinear function, right? We cannot segregate the points which are in red region from the blue region. Now, I'll just give you an intuition how we can generalize this with the help of very small neural network, right? So in the left hand side, you see a figure, this one. So what I'm having is, this is a very small neural network, and this network is having total 3 layers. One is this layer. You can consider this is also a neuron. 3 layers. This is called input layer. This is called hidden layer. And this is called output layer. Okay. Now what is happening? Let me illustrate this in a sequential way. I'm having input x1 and x2, right? This x1 you can consider as screen size, x2 you can consider as cost, or whatever parameter you want to consider, you can consider this. Now, this input we are feeding to this neuron, right? And this input also we are feeding to this neuron. The weight associated with this x1 is W11, the weight associated with x2 is W12. Okay, and there's a threshold term which we are applying here is B1. Okay, so B1 is applied to this neuron. Okay, now for the sake of terminology, just understand that this is also called as bias. Right? So far we have been seeing this as threshold, but if I say that this is bias, just consider that these two are one the same thing. Okay.
Bias and threshold.
Bias and threshold, they both are same thing.
Okay.
Okay. All right. So what will be output at this point? Let me call this output as H1. Okay. Okay. So this H1, you see, this is a function of x2 and x1.
Yeah.
Right. And what is this, my H1? My H1, if I am applying here sigmoid as an activation function, it will be 1 upon 1 plus e raised to minus W1 x1 plus W12 x2 plus B1. This is nothing but sigmoid neuron thing. Right?
Yeah.
Similarly, for this neuron, let me call it as H2, I can compute the output.
Yeah.
Right? This is also sigmoid neuron. So we have computed H1 and H2. Now, this H1 and H2 will act as an input for this neuron. Right? So let me call this as here y cap. Yeah, y cap I've already named. Okay. So this becomes my new input. Let me call it x1 dash. Let me call this x2 dash for this neuron, right? And the weight associated is W21 and W22. Okay. Now, same thing if I'll apply like the way I have done here, you'll get this expression. This y cap will be this expression. I'm just putting the values of H1 and H2 as sigmoid function. Right? Now the final output which I'm getting, y cap, which is this big expression, you'll see that it is nothing but the broader paradigm is same. It's just that we have added more number of neurons, we are having more number of weights, and we are having more number of biases. Right now, this big thing, if I play with W1, W12, W21, W22, and B1, B2 with some brute force approach or with some principled approach, then I'll be able to generate some, decision boundary that can segregate these two circles.
So only changing W21, W22, or also changing W11, W12, W13,
All the weights, all the weights. Yes. See, in any neural network, you'll have mainly two learning parameter. One is weights, the other is biases.
Yeah.
Okay. So now this problem is effectively reduced to getting the optimal value of this weights and B that will come up with a function that can segregate these two circles. Right. So this is how neural network works. If you look from the top perspective, it is nothing but, we had first of all one neuron, it took the input, it did the weighted sum, it applied activation function. Similarly, this neuron does the same thing. Now the output of these two neurons becomes the input for this, right? The output got propagated to the other neuron, and finally we'll have the output, final output. And this output is this big expression. And from this big expression, we can get this complicated function. Okay. Till now, is it clear? This is a question I would like to attempt, but not in the class. You can take the screenshot of it and paste the answer of this question in the group. This would require some mathematical computations, some multiplications. So just take the screenshot of this and answer the questions in chat. Okay. Now, this network we have seen, this was specific for solving this problem, right? But now let me tell you how this neural network operates in detail for generic problem. Okay. So typically any neural network, it will have three type of layer. As I already mentioned, it will have input layer, it will have hidden layer, and it will have output layer. Okay. So you see here in my input layer, I'm having three neurons here. In hidden layer, in hidden layer, I'll have three, and output layer, I'm having two. Okay. Now,
that's two hidden layer, right? H1 and H2.
Wait. No, only, yeah, two hidden layer, 1 and 2. You can consider this as input layer.
Okay. So these hidden layer can be as many as they can, right? Okay.
Yes. All the things that you are seeing here in this architecture, it's entirely customizable. You can put n number of hidden layer. You can put n number of neurons in each hidden layer also.
Okay.
Right. Now the thing is, we are seeing this as a feed forward network. So what is meant by feed forward network is the direction of your movement will be always unidirectional. For example, the input x1, x2, and x3, it can go in the forward direction only. It won't be situations where the output of this neuron can be fed back to itself. Right? It won't be a reverse flow. So that is why it is called feed forward network. Now the next,
can you repeat, Ashutosh, what do you mean by it is forward? Like, why would it be ever backwards? The x1 is always applied, right, to the
x1 will be always applied. That the direction of propagation will be unidirectional. It will always go from bottom to top. It will not be situations where the output of this neuron will be fed back to itself.
Okay.
It in at least in case of feed forward network, you'll not see that the output of this neuron will be fed back to the one layer which is below of it. It will always go from bottom to up.
Yep.
Okay, that's why it's feed forward network. Now the point is, now we have to create an interconnection between these neurons, right? So each of the input from one neuron can be fed to all the other neurons. So you'll see here in the next slide, from this x1, you'll see this x1, my input is going to this neuron also, this neuron also, this also. Similarly from x2, this also, this also, this also, right? Now this is one hidden layer, this is another hidden layer. Now each neuron will have two things, right? So what happens at this neuron? It takes first of all the weighted summation of all the input, right? And that is called pre-activation. So two things will happen here. Pre-activation and then activation. Okay. So what happens in pre-activation is it will do the weighted sum of all the input, right? So it will be w1x1 plus w whatever weight I'll have here, multiplied this x2 likewise. And after that, the next operation happens is activation, where we actually apply sigmoid function on top of the summation, right? And this will happen for all the other neurons also. Now let me define some of the terminologies that will make our life easier and easy to understand the upcoming concepts. See, whenever I do like weight 1 1 1 0, right? It means that here the first one, here the first index, this one, it means that it defines the layer number, right? The second index defines the neuron number, and the third index defines the input number, right? So if let me clear this one first of all, right? So here if I write this w what 1 3 3, what this means is I'm talking about the weight which is associated with neuron which is present in my first layer, right? The sequence of this neuron is third, 1 2 3, and this is corresponding to third input, 1 2 3. Similarly for this one, what will be my weight?
1 1 1
1 1 1, right? So this nomenclature is clear.
Yeah, so the middle one will be 1 2 2, right?
The middle one be, yeah, w 1 2 2 for this one, right? If it is taking from this one, then w 2 1
W21
w 1 2 1. I'm talking about the first layer, that's why 1. I'm talking about the second neuron, that's why 2, and it is taking input from first neuron, that's why 1. W1 2 1, right? You say each neuron is taking input from all the neurons which is one layer below of it.
So 1 1 2, what will be 1 1 2? 1 1 2 will be the first layer, first neuron.
Yeah, first layer, first neuron, which is taking input from the second neuron, right? So this one will be 1 1 2.
So W112 is the weight associated with X2, right?
Weight associated with X2, which is going to this neuron.
Yeah, to that neuron.
Because this is also associated with X2, this is also associated with X2, right? But that's why it becomes important to specify the neuron number also.
Yeah, so 112 is associated with X2 for first neuron. Similarly, you will have, other these numbers associated with respective neurons.
Yes. Right. I have written here a brief description about it. So if any point of time you feel like it's getting confusion, then you can have a look. Till this part, it is clear?
Yeah.
Okay. I know it's not very easy to take in the first go. You'll see this will even become more complicated. Okay. So first of all, we have to calculate what will be my output in my first hidden layer, right? First of all, I have to compute what will be output in my first hidden layer. So what this is it is basically consisting of 3 neurons, right? Right. So obviously, whatever you'll have in my first layer, it will be a vector, and the vector will have 3 elements. One output coming from, one output from each of the neuron. Are you able to understand here? See, what will be your, let me call it as here, Z1, Z2, Z3, right? What is my Z1? Z is the weighted combination of all of my input with weights plus bias, right?
Yeah.
And after that, if I'll apply a sigmoid function on top of it, I'll get one real number that will vary between 0 to 1, right?
Yeah.
I'm writing that real number here.
Okay.
Okay. Similarly, for this Z2, what it will be? It will be weighted combination of all the input. I'll apply sigmoid layer, and then it will be a real number between 1 to 0. Similarly for Z3 also. So if I have to represent this thing in a form vector, I can write in this way. A vector which will have 3 real number that will belongs to set. Okay.
Yes.
For the next iteration, for the next row, these 3 will become input for this layer.
You mean for the second layer?
Yes, for the second layer. Whatever things that we have done calculation for the first layer, it will become input for the second layer now. And you have to repeat the same process. Okay.
And then there'll be new associated weights, right?
Yes, those will be new associated weights. So here it will be like, if I have to, this line, if I have to talk about, I'll say W. Can you help me here? What will be W2, 1, 1 weights which associated with second layer, right? For the first neuron coming from the first neuron of my input layer. Is it clear?
Yeah. What will be
weight for this one?
You mean for B2?
For this one. No, for this one.
W3.
W3. How W3?
Oh, sorry. W.
This is hidden layer 1. This is
W2.
2.
Yeah.
W2.
2, 3, then 3.
W2, 3, 3. Yeah. That's correct.
Why again 3? W
Because
second
it is
layer.
First of all, layer number is 2.
Yeah.
Within this layer, what this is third neuron, 3.
Yeah.
And this neuron is taking input from a third input, 1, 2, 3.
Yeah. W2, 3, 3. Yeah.
Right. So that's why I'm talking about this line. Okay.
So Ashutosh, like this is the case of just 3 neurons, right? But when this structure becomes complex, then the naming conventions become even more complex, right? Like
yes, of course. I'm just have here taken example of 3 neurons. You can think of a neural network where you'll have thousands of neurons. So obviously we are not going to do this through pen, paper, and all those computations manually. For that, we're having a framework. what we need to do is we just need to specify our input. We should know only our input. Okay. We should know what kind of activation function that we want to apply on each layer. Right.
Yeah.
And we need to define the architecture. So if I say feed forward network, then automatically system will create a feed forward network where no backward movement is allowed. This is a feed forward network because the movement is upward, right? So it will create some architecture like this. Initially, this W values will be all unknown, right? And then it will start the training process. It will it will apply certain algorithm. We'll see what that algorithm is, and it will find the value of W, appropriate values of W's and B by itself. All right. Our job is just to know our input, just to know our activation function, just to learn a little bit about algorithm, how it is doing the training part, and need to know what activation function I'll be applying in output layer. Okay. So similarly, in the output layer also the same thing will happen, right? If I'm applying a sigmoid neuron, so here I'll be getting some value that will belong to set of real number, and that will range between what, 0 to 1.
Yeah.
Similarly here also that will belongs to set of real number, right? So this process is, practically if you see, this is very complicated because it is in practical problem you'll see a very complicated network. My intention is not to train you so that you do it by pen paper. I just wanted to give you a feel how the data flows, how the input of one neuron goes to the input of another neuron, and that's what happens in our brain also, right? The input of one neuron flows to the other neuron, and likewise it happens for thousands of layers, and after that some output is created. Okay. Anyone is having any questions till here? Okay. So here
I maybe you might be explaining it in the future, like now, but I didn't understand this f of x equal to HL OAL. Okay.
Yeah. Yeah. So it's just the matter of naming convention. Okay. So what this AI, so I'm writing here in generalized form. I have explained the computation line by layer by layer. So this is in generalized form only. So what is meant by AI1X? That means what? The activation layer. If I define I equal to 1, let's take an example and then this will become clear. If I is equals to 1, right? That means I'm talking about my this layer, activation layer of my first layer, A1. Okay. WI. So WI is what? W1. That means it is a matrix of all of my weights. Right now we have seen weight associated with each of edges, right?
Yeah.
So I can write all these weights in form of a matrix, right? And that matrix is written as W1.
Yeah.
Right. I'm taking input from my previous layer. That's why HI minus 1.
So right? The H is nothing but x1, x2, all right?
Yeah. So here what I'm doing a dot product of my W and X, weights and my input. That will give a weighted sum, right?
Yeah.
And then I'm adding this with BI. BI is what? B1. B1 is what? My biases for my first hidden layer.
Yeah.
Right. So this part is clear?
Yes.
This thing we have to do for all the layer until we reaches the last layer. Okay. So for last layer also the process is same. It's just that in last layer the activation function we have to choose based on the task we are trying to solve. Right? For the rest of the layer, you can think that the activation function you'll be applying is sigmoid. But in the last layer, it may be sigmoid, it may be something else. And that will depend upon the task we are trying to solve.
So for every layer, initially for all the layers, except for the output layer, the G will be the activation function, same everywhere.
Yes, sigmoid.
Okay. And then in the final layer, we may apply a different function, a sigmoid or something else.
Yes. Actually, even in this layer also, you can, instead of sigmoid, you can put some other function also. But since you're already familiar with sigmoid, and give an example of sigmoid. As I mentioned, everything you can customize. Right?
Okay.
All right. Then okay. Now let's build our knowledge on top of things that we have already discussed. Here I have taken one example. Okay. So now I'm no longer talking about W11, W22 because it's not really notation wise feasible to write weights for each of my connections, right? So I have defined W1, right, which is the matrix of all the weights.
Yeah.
Right. Similarly, I have defined a vector which is what? Which is the collections of all of my input.
Yep.
Okay. So first, if I have to compute A1, I am doing dot product of Wx plus B, that we have what we have just seen. Right. Then I'm applying an activation function, which is a sigmoid here. So that is represented by G. And this will give me an H1 of my first layer.
Yeah.
Right. Yes. So similarly, I'll be computing this for the other hidden layer also. Right. Yes. And at the end, when I reaches the output layer, same thing will happen. It's just that my activation function might vary, but if I have to define it, define the operations, it will look something like this. Let me try to simplify this one for you. Okay. So this is what this part. This part is nothing but what? This is A1. What is this? This part here is nothing but, this is
A2.
H1, right? H part. I have applied G here, right? G.
So GW1X plus B1 is H1, right?
GW1X1, yeah.
And W2G, that whole of the will be H2.
X2 from
H2.
yes.
Right?
Yes. So see, this is nothing but, so don't get confused with the notation part. It is nothing but from how I'm relating output with my input. That is what I'm representing here. Right, but do not try to think it as a formula, because it will change if I'll change the number of neurons, if I'll change the number of layers.
Yeah.
It is just to show that how the input from my input layer has propagated till output layer. Okay.
So what I'm understanding is, from the very first layer, like we have the standard formula, right? Wx plus B1, but that whole thing is becoming like X for the second layer.
Yes.
Then its output is again becoming the whole thing is becoming X for the next layer, right?
Yes, exactly.
Okay. Yeah.
Exactly. Okay. All right. Yeah. So this is a repetition of previous slide, but the only difference is it is a bit more in detail. Okay. Now see, as I mentioned that this network designing depends upon the type of task we are trying to solve, right? So this is one neural network, and this neural network is trying to solve a problem of classification, right? And the input which we have given to this neural network is nothing but an image of apple, right? So output, what we are supposed to get is, we are supposed to get probability, right? So we have total 4 labels, apple, banana, orange, and grape. Okay. So what I should get is, in my output layer, I should get my probability value 1 corresponding to apple and 0 for rest other. Right? Then only we'll see that this network has identified this image properly, correctly. Are you able to understand?
I'm able to understand, but so far, we have been talking about y and y cap, right? Y is the known output and y cap is what you're predicting. Now you have introduced a term label. So this label is it y cap only, or label is something different?
Label is nothing but it's a target only. Target, label, y cap, they all are, same thing. Of course not, y is not equal to y cap. Y is the true label and y cap is the predicted label.
Okay.
Right. So just think it as a target. And the problem is, there are multiple terms for a single thing in machine learning or deep learning. That's why sometimes it's become confusing. Okay, anyways, right? So this network is trying to do a classification task. This other network you are seeing that it is trying to